Dear members of the conference, we present to your attention a report on the subject optimization of electrocontact welding wear-resistant functional coatings regime and the use of engineering industrial wastes. The problems of improving the quality of the resource of machines occupy an important place in mechanical engineering, and therefore, there is a high need for the development of technologies aimed at improving the technical and economic indicators of production. Such technologies can be applied both for the restoration of worn parts of machinery and equipment, and in the manufacture of new ones. Resource-saving technologies are especially relevant for use in the production of agricultural machinery parts operating under conditions of abrasive and corrosive influences, accompanied by increased dynamic loads. The direction of development of such technologies is the creation of coatings on the working surfaces of machines that provide, first of all, high wear resistance and corrosion resistance while reducing the consumption of expensive materials with the considered, required, properties. One of the effective and promising ways to obtain such coatings on the working surfaces of parts is the method of electrocontact welding of compact materials. This technology makes it possible to obtain coatings, including from waste from tool and machine building production, which further reduces the cost of purchasing materials and meets the current trend aimed at developing recycling technologies to reduce harmful emissions into the environment. One of these technologies for creating wear-resistant coatings is presented. With this technology, a wear-resistant coating was obtained on the zone, toe, of the plowshare exposed to the greatest abrasive wear by electrocontact welding of unusable hacksaw blades made of steel grade 11R3M3F2. For the realization of this procedure, it was proposed to use the wastes of machine building, or other branches of industry, in the form of strips or wires made of structural, carbon tool, alloyed tool, or high-speed steel, manual, machine, strip, and jigsaw blades, files, broach files, drill bits, and their debris, as well as the cut and chipped ends and flash formed in the tool-making production. Functional coatings are obtained in the course of welding of these wastes to the restored and hardened surfaces by step seam heating at a temperature between the tempering temperature and the melting points of joined metals as a result of the transmission of pulses of welding current with a current value from 4 to 12,000 amperes under a voltage of from 2 to 5 volts with simultaneous application of pressure and supply of coolants into the region of the joint. The implementation of this technology was made on an electrocontact welding machine with a resistance of 0.11110 rmdtl. The preliminary abrasive blasting operation of the parts surfaces was carried out on the DIMIT 405 cold gas dynamic spraying unit. The samples were cut off using the LC300 metallographic cutting machine. Micro-hardness was measured using a Metalab 502 hardness tester. The hardness of the samples was obtained by the Super Rockwell method using the N scale of small loads on a TH320 hardness tester at a load of 147 newtons. Where resistance of obtained coatings was determined on IMO1. Samples were weighed before and after the tests on the scales of VL120C. Before welding, the connected surfaces of the main and additive materials were subjected to abrasive blasting operation. Abrasive blasting operation of the surfaces was performed with DIMIT KO416 corundum powder. Stamit 1301 nickel-based amorphous tape solder was used as an intermediate layer. As an additive material, the following were used: spent hacksaw blades made of steel grade 11R3M3F2 with a thickness of 2 mm. As well as steel strips with a thickness of 0.5 mm made of steel grade 65G, U12A, 50HFA. As a basis, samples made of strips of grade 65G steel with a thickness of 12 mm were used. For reference, used sample made of 45 steel. Formulas for calculating the mode of electrocontact resistance welding are presented on the following slides. First, the current value, the welding current time and the optimum compression force of the roller electrodes. Next, welding speed. The area of the filler material through which the current passes during the entire pulse, feed and performance. The hardness of the 11P3M3F2 steel sheets before they were welded in the initial state was 57.08 HRC. In the zone of thermal influence, tempering, After the electrocontact resistance welding decreased to 51.4 HRC, inside the welding spot hardness, rehardening zone, hardness increased to 64.0 HRC. Similar data were obtained when analyzing the results of measurement using the micro-Vickers method. At the welding spot the maximum average hardness value is 904 HV, in the tempering zone 595.6 HV, in the zone with the initial structure 804 HV. Wear resistance studies have established that the coating obtained by electrocontact resistance welding through a tape amorphous solder 1301 carbon steel tape U12A has a wear resistance 1.48 times higher than the coating of the tape 50HFA, as well as 4 times greater wear resistance than steel 45. While the wear resistance of steel 65G after electrocontact tempering is 2 times higher than steel 45 and higher than steel 65G 1.5 times. Wear resistance of coatings of steel 11R3M3F2 on the basis of steel 65G obtained in the calculation values for the hard electrocontact resistance welding mode is 7.3 times higher than the reference steel 45 and 1.7 times higher than that of coated samples of steel U12A obtained by this method with comparable hardness on the HRN15 scale. It is certain that the main parameters of the ECW process are the welding current, the compression force of the welding electrodes, the pulse duration and the pause between pulses, the cool and flow rate, the welding speed and the process productivity. The calculation of modes of the process of applying functional coating by electrocontact welding of useless hacksaw blades made of steel grade 11R3M3F2 has been made. It is seen that the productivity of the ECW process in hard mode is 6.73 times higher than in soft mode. Therefore, to implement the process we choose the hard mode. It was found that the wear resistance of 11R3M3F2 steel coatings on a 65G steel base obtained at the calculated values of the ECW mode is 7.3 times higher than that of normalized 45 steel. Thanks for your attention.